good. Okay. I'll turn on the light. Although we had this issue with this room, right? Yeah, turned on. Let's see. Is it good in the back? Too bright? No? Okay, let's keep it this way for now. This room also needs some air, no? Am I the only one who thinks this way? Seems a bit. Air quality seems low. Okay, I think we can get started. Do we have any announcements?
So at the end of, after like the end of this lecture, we're going to release the paper options for you. You can find them on our course page, and also, but we'll be also send you an announcement for this. And so you will be given a list of papers and a deadline for you to let us know which are your preferences. So you will have to vote for the paper you want the most, you want the least, and we will try to make sure we take into account the preferences and assign with specific paper. So the paper will be out today. I mean, they're already online. You will be able to see them at 6. The deadline should be around Monday with your references. And then we will make the assignments very quickly so that you have all of you more than 2 weeks to prepare for your presentation.
Sounds good. Any questions?
We start on April 2nd. Is the
yeah.
You will soon be.
Yeah, we will soon know. Okay, thanks, Konstantina. Okay, today I'm going to give an overview of some of the papers that you may select. Well, some papers that may be related to this topic at least, which is memory robustness. You kind of saw a brief overview of it when I talked about memory-centric computing, but I want to do a deeper dive. Say it again. Is it too bright for you? I don't know. For me, it's too bright, but people say it's okay, right? A bit bright? Who votes for a bit bright? Who votes for it's okay? Okay, a bit bright wins, I think. You can turn it off. Now it's going to be a bit sleepy compared to it's okay. That's the trade-off. With this room, you can never win. But there are better rooms. Anyway, hopefully people won't sleep. Okay, we already discussed RowHammer and similar issues, but I want to give you a deeper dive on this because it's a very important and exciting topic these days. And there are a lot of issues in memory robustness that I think we should deal with going into the future. Zoom always has its own, yeah. Okay, I also give this talk at different places and I start calling it like fantastic bit flips and where to find them and how to fix them. Does that sound good? Does that make you think of some things? You probably have read the novel or probably watched the book. Watched the book, it sounds good actually. Well, these days you can watch books, right? You can feed a book. Or better yet, you can ask an AI that plagiarized the book to make a movie for you. And you can watch it and see if it's as good as the movie itself. Probably not. Anyway, that's kind of a joke, but it's also a bit sad that things get plagiarized. We used to take plagiarism a bit seriously. Now AI is plagiarizing everything and feeding that to people. I wonder where that is going to go. Okay, anyway, we're not going to talk about that. We're going to talk about bridges that get bit flips. And this is what happens to them and then when they get bit flips. Does anybody know what bridge this is without looking at? Okay, this doesn't give you a lot except the state in the US. Anybody knows where this is? This is in the Washington state where I used to live. And this is the Tacoma Narrows Bridge. And I crossed the new version of it, which is a double bridge, which actually is more reliable, hopefully. But this is what happened to it in 1940. And it's essentially got a bit flip. And this is important infrastructure. And bridges are, no question, important infrastructure. But computing today is probably the most important infrastructure that we have. We want computing to be robust. I think this picture also points to some people that are sitting on something that they rely on, some infrastructure. And if a bit flip happens over here, these people will not be very happy. And I think I saw a picture of this, not necessarily plagiarized, but adapted to Time magazine. Was it the Time magazine? I don't remember. And it had people, like some famous people who are building AI infrastructures of today. And I thought about that and I said, oh, if they get a bit flip, then they'll be doomed. Well, I'm sure they'll be okay, but the rest of the world may be doomed. Anyway, essentially, robustness or security is about preventing unforeseen consequences such that that bit flip doesn't damage things, let's say. I like this picture also. Anybody knows what this is? Yes? Who knows, I guess? Yes? Yes, it's Mr. Bean. Yeah. Yeah, Mr. Bean is driving his self-driving car over here with whatever he uses to control his self-driving car. And today we're relying on these self-driving cars. And if we have bit flips in them, maybe we should not be relying on them much. Okay, basically we're building a lot of infrastructure. And this infrastructure is supposed to make our lives better. It's not clear if they can make our lives better if they are not robust, essentially. So a big challenge and opportunity we have for future in design of systems in general is making systems robust to failures, to essentially harsh conditions, wherever they may be used to work at. And robustness actually has multiple aspects: reliability, security, safety, availability. All of those are part of robustness, essentially. That's why I think of these bit flips, let's say, as robustness problems, because they are, in the end, some sort of reliability problem, and they affect dependability of a computing system, but they also affect security, they also affect safety, they also affect availability and predictability of a system. So robustness kind of encompasses all of those aspects. That's why I like this term much better than any of the individual terms. Some people, for example, say RowHammer is a security phenomenon. I vehemently disagree with that. It is security, related to security, no question, but fundamentally it's a failure mechanism that affects all types of robustness. Okay, so you've seen RowHammer, so I will not go through this in a whole lot of detail, but essentially you can induce these bit flips in commodity DRAM chips, and all recent DRAM chips are vulnerable. And this is the first example of how a simple hardware failure mechanism can create a widespread system security vulnerability. So there's a lot of like media articles that says some interesting things like this. Forget software, now hackers are exploiting physics, which is true, actually. It's not a bad characterization of RowHammer. And you've also seen some of these papers that I flashed at you in the past. So we've been looking at memory system design for a long time, and we've been looking at issues in technology scaling in memory, especially DRAM and flash. And we've been seeing that it's very difficult to handle these issues because they're technology scaling problems as memory scales to smaller technology nodes so that we can get higher capacity, higher density, so that we can satisfy the requirements that we have in data-intensive applications. It becomes less and less reliable, less and less robust, essentially. And we've argued, as you know from last lectures, that to solve these problems, we should really have an intelligent memory system where you can design the memory system together with some computation mechanisms. And these computation mechanisms allow you to, or ensure that the memory still operates reliably, even though the underlying substrate, underlying hardware is less and less reliable going into the future. But if you have computation mechanisms that detect these reliability problems, you can still get the right answer, even though the hardware becomes worse and worse. Okay, that's the idea over here. And we keep writing papers about it, as I have flashed at you last time. So we're going to delve a little bit more deeper into these issues in DRAM today. And as I said, there's a technology scaling problem. When you design DRAM, DRAM was developed in the 1960s, and it was not exactly like this at the time, but the basic ideas are similar. You store data as charge in a capacitor, and you interpret that charge level as 1 or 0. And in order to be able to do that interpretation or sensing, you need to access the charge level using an access transistor, using that word line over there. And that perturbs the bit line, and you sense the perturbation in the bit line to determine whether you have a 0 or 1, charged or discharged, right? So for this to work correctly, all of these mechanisms that I described should work reliably or robustly. For example, capacitor must be large enough for reliable sensing, right? If it's too small, maybe it's not going to share enough charge with the bit line, so you cannot sense it. You cannot sense it reliably, right? The access transistor should be large enough and robust enough so that you don't leak the charge too frequently, and you can also get high retention time. Yeah, and people have been writing papers and also projecting that scaling the size, the feature size of a DRAM cell below some number is very challenging. And that has been true, basically. This, for example, ITRS, International Technology Roadmap of Semiconductors, which was a body who was projecting what will happen to semiconductors for many, many years. I think they renamed themselves. I don't know their name right now, but essentially they were projecting in 2009 that reducing the size of a DRAM cell, the feature size, below 35 nanometers is challenging. And they were right. Today, we're much closer to 10 nanometers, for example. We're not below 10 nanometers yet, as far as I know. Anybody knows? Not yet, I think. But we've improved capacity, but it came at a cost, essentially. Essentially, this means that DRAM capacity, cost, and energy are hard to scale because all of them are affected by scaling in the end. So these are some real examples. This is kind of a virtual picture of DRAM. The capacitors actually, I think I like this picture a little bit better. The capacitors actually look like this. You can see that it's a three-dimensional structure. If you think about it, it's etched into hardware. And then you have bit lines that look like this and word lines, etc. So you can see a lot of videos and a lot of pictures. So the capacitors are actually, it's very hard to manufacture these capacitors. And that's one of the reasons why we're having the scaling problem. And people are investigating new ways of doing it, new ways of manufacturing, new materials. So there's investment in that area. Okay, so if these things are vulnerable to noise and they can actually operate unreliably sometimes, and they're all of these structures are vulnerable to noise. And as you reduce the size of the cell, meaning reduce the size of the capacitor, reduce the size of the access transistor, there's less charge, and these reliability or robustness properties become more difficult to maintain, then you get bit flips, right? And we have analyzed the impact of these bit flips at a high level at the data center scale. This is a work we did with Facebook a long time ago. I think there are fewer and fewer studies like this. There should be more and more. Actually, there are some studies, but I think there needs to be more and higher scale and more detailed, as opposed to repeating the same thing again and again. But basically, we found out in this study that was published in 2015 that the server failure rate you get in all of the data centers, all of the computers that are employed at Facebook at the time, and this was a lot of computers at the time. Today is much, much larger, of course. So the scale of the study is very large. Facebook didn't allow us to put the amount of memory and number of servers that we observed because they thought this was too disclosing their size of infrastructure. I think they have a lot more things to worry about right now, like a lot of privacy issues and a lot of messy things, let's say, with Meta. But essentially, what we observed was there is a strong correlation between the density of the DRAM chip employed in the server and the failure rate of the server. So it's more likely that servers that employ denser DRAM chips, they're more likely to fail. They're more likely to get more errors. So there was a strong correlation. And you can read the paper. There's a lot of analysis of this. There are a lot of other results in the paper also. And these studies are interesting to demonstrate that things are getting worse, basically, at the system level. And also, we proposed some mechanisms to reduce that and tested it as in a cluster. And it may work, but things are not easy to manage, basically. Okay, that's the paper. We also did a lot of studies to really understand what's going on at the. So if you do that sort of study, that like what I mentioned, observe what's going on in a production data center when it's running production workloads, record the memory errors that happen, try to figure out what's going on. You have very limited control, right? We clearly cannot change the workloads that are executing. We clearly cannot change the access patterns. We cannot change the conditions as much, operating conditions. We cannot, for example, test at 80 degrees Celsius because you don't want to run a data center that's at high temperatures. in general. Well, a data center memory, let's say. You're not going to run the data center room at 80 degrees Celsius, hopefully. That would be terrible. But basically, we wanted to have more control to understand the sources of these errors. And for that, you really need to have control. So you need to do controlled experiments as opposed to observations from a running system, right? And if you want to do controlled experiments, you need a flexible system that can change the conditions under which memory operates or memory is accessed. And you want to figure out what are the causes of these bit flips. And that's exactly what we built. This is the FPGA-based infrastructure that I mentioned last time. We'll go more into it, which has a soft memory controller that you can program such that you can change the timing parameters, voltage, etc. And this was where we did a lot of the RowHammer experiments on. And I've already shown you these in the last memory-centric computing lectures. These are open sourced. People have been developing things based on them. In fact, there's a DRAM workshop that's coming up at S+ in a couple of weeks. And this is the newest version where we did a lot of experiments on HBM and as well as DDR4. So these are some examples over here. And this is the lab that we have that I showed you also. So you can do a lot of interesting things over here. And one of the major reasons why we built this infrastructure was to examine the scaling problems. In fact, technology scaling was the motivation for why we built this FPGA-based infrastructure. It was a lot of investment. It took some time. And there was no similar infrastructure that existed at the time. Still, no similar infrastructure exists, basically. Basically, this what you see over here doesn't really exist anywhere else, as far as I know. Even those memory companies that should have more of these, I think. But anyway, one of the reasons why we built these things, this infrastructure, was to actually understand one of the scaling problems in DRAM, and that's data retention. The theory is that as you reduce the size of a cell, the amount of charge in the cell reduces, and also the access transistor reduces. So both charge reduces and access transistor becomes leaky, especially under variation. These get amplified. And the theory is that you need to refresh cells more frequently. And that theory holds, actually, in real life. The refresh rate of DRAM has reduced, or a refresh rate of DRAM has increased over time from many milliseconds to smaller milliseconds, like 64 milliseconds. Today, at DDR5, you have 32 milliseconds. And we said solving this problem at a lower level is very difficult. So we want to look at architectural solutions to the problem, meaning design an intelligent memory controller that refreshes memory less. Right? That's the idea. And I still like this sort of ideas. How do you get rid of the inefficiency in systems? Because refresh is really an inefficiency, right? If you can get rid of some of the refreshes by exploiting the device structure or device properties with an intelligent controller, you can actually gain performance, efficiency, quality of service, everything that we care about. And this is one of the things that we wanted to study with this work. Essentially, it was known that there's variation in the retention time of DRAM cells. And this is what the variation kind of looks like. Some cells need to be refreshed every 64 milliseconds, very small set. But most of the cells you can get away without refreshing every 64 milliseconds. You can refresh them at 256 milliseconds. So this is a very realistic picture in terms of which rows need to be, what fraction of the rows need to be refreshed at what rate. But what happens in real systems is you don't take this into account. You refresh everything at the worst case refresh rate, every 64 milliseconds. Okay, that's what happens in existing systems. Our goal was to actually refresh rows at the rate that they really require to be refreshed at. That's the idea of this RAIDER, retention aware intelligent DRAM refresh paper. I mean, there was a mechanism that's proposed that I'm not going to go into. But what we wanted to do is really understand how we could really implement it. Unfortunately, it's not as easy to implement. This paper is beautiful because it doesn't talk about some of the implementations, but it's good to still do the research to show the benefits if you can implement an idea. Then the question becomes, how do you implement it? And to figure out how do you implement it, we built this infrastructure. And we found out that it's not easy to implement because this retention time of a DRAM row is not just dependent on the location of the row, but also a lot of other things, like the stored value in the row data pattern, and also some quantum-like effects like variable retention time. And all of those are becoming worse. Data pattern dependence and variable retention time are becoming worse with technology generation. So figuring out how often you need to refresh a row is becoming more challenging, while the frequency of refreshing a row is also increasing at the same time with technology scale. So we wrote a bunch of papers. This is the Raider paper. This is the first paper that used the infrastructure that we built actually to understand the retention time properties of modern DRAM devices. It basically showed that retention time is getting worse, variable retention time is getting worse, data pattern dependence is getting worse, and it's very difficult to build these intelligent mechanisms. And later, actually, we did a lot of studies to build it in a much better way. So there are other works that are much more implementable to enable this. So this is kind of a history of why we built this infrastructure. And you can find more information on DRAM refresh and data retention on some lectures, which you may have attended. At the same time, we were doing a lot of studies on flash memory. This is multi-level cell NAND flash memory at the time. Clearly, this is really important memory that has enabled a lot of mobile devices to even work today with cameras, for example. And we wanted to understand the scaling properties of these NAND flash memories, because again, a similar issue exists over there. As you reduce the size of a storage cell, NAND flash memory cell, it becomes more vulnerable to noise. And there are many different types of noise effects, including retention problems, including read disturbance problems. And we built an FPGA infrastructure to actually test those issues and understand the error mechanisms that go into NAND flash memory, and also develop mechanisms to correct those errors. So there's a long string of papers that we've written over many years on this topic. Now, one of the reasons I'm telling you this is there's actually other memories that are also very interesting. It's good to build infrastructure for them. And we wrote papers. And the other reason I'm telling you this is because we were actually inspired by some of these studies that we did for flash memory to understand whether DRAM also has these issues. So in research, it's good to have a broad perspective. If you're looking at memory X and memory X has some issue, it's always good to ask the question, does memory Y also exhibit a similar issue? Right? For example, in our papers, this is one paper, this is another paper that we published at the Intel Technology Journal, an invited paper that goes into a little bit more detail. But basically, we found out that one of the major error mechanisms in NAND flash memory is retention errors. But another major error mechanism is the read disturbance errors. So whenever you read a page in NAND flash memory, you disturb all of the other pages that belong to the same block. And this turns out to be not so good, clearly. In NAND flash memory, the memory controller can correct some of those errors. And later works, we actually developed some other mechanisms. But we found out that this is actually a worsening problem in NAND flash memory. And then we asked the question, and this is one of the papers that you might be interested in reading. It's not in your list because it's a very long paper, like 30 pages or so. And then we asked the question, do similar issues exist in DRAM and how bad they are? Right? And that's one of the reasons why we came to RowHammer, essentially. And the answer was basically yes, similar issues exist. You've seen the slide before, so I'll go through this relatively quickly. But essentially, read disturbance in DRAM occurs because you're accessing, cells are too small and too close to each other. Whenever you're accessing one cell or one row of cells, you're really inducing some noise on cells or rows around the row that you're accessing. So if you want to access some row, you open that row, you apply high voltage. And that action itself causes some disturbance. And if you want to close that row, you apply low voltage. And this toggling, activate precharge toggling that you keep doing repeatedly causes some noise in adjacent cells, okay? There are device level papers that are written on this topic. If we have time, we'll get to some of those. But essentially, it's a disturbance problem. You're disturbing based on some noise. Okay, so we call this the hammered row. We call this the victim row. And we showed that if you are able to do this hammering, activate precharge repeatedly, many times before the cells get refreshed, some cells in victim rows fail, meaning they get corrupted. They lose charge little by little. And eventually, you cannot recover the data value or charge that you stored over here. And these were our original results in 2014. Well, actually, the paper got published in 2014, but we had these results in 2012. We just improved them over 2 years, let's say. And we found out that we basically showed evidence that this is a scaling problem because we didn't see this effect, or we weren't able to induce bit flips in chips that were manufactured before 2010. And we were able to induce bit flips in all of the modules or chips that were manufactured between 2012 and 2013 from all major manufacturers. And there are three major DRAM manufacturers, as we discussed: Samsung, SK Hynix, and Micron. At that time, we were not naming them, but in papers right now, we're naming them. There's no reason not to name them at this point. We'll talk about the story of that also a little bit. Yeah. So there are actually interesting questions over here. Like we weren't able to induce bit flips in earlier chips. And one of the reasons was we were not, because the cells are larger in past chips that were manufactured, and cells are farther away from each other, the number of activation pre-charge pairs, the number of hammers that you need to do is too large. Right? You cannot have enough of those fit in the refresh interval. So I think in DRAM you have 1.4 million activations you can do within a refresh interval, under some conditions, of course. And we were able to induce those bit flips with 139,000 activations, probably in the best case, or in the worst case from a scaling perspective. But for older chips, we were not able to do that. Okay, so that's one of the reasons. And also, we were not maybe using the best patterns. This will become more important. Best hammering patterns. So one pattern is, for example, hammering one row, keeping on hammering one row. But if you actually hammer two rows and sandwich one row in between them, you cause a lot more disturbance to the row that's sandwiched between two rows that you're hammering. Okay, so maybe these results will change, but it doesn't matter right now. All of the chips are so vulnerable that the results are much better than what we demonstrated like 14 years ago or so. Okay, so why is this happening? I think I've said all of these. I will not go into more detail. You have a lot of interference, cell-to-cell coupling and interference. And there are a lot of device-level reasons for it. But again, I will not talk about that. And the issue over here is these cells are exposed directly to the programming language or the operating system. Basically, main memory, if you get a bit flip, your program gets immediately affected because your data structures are in main memory, right? Operating system data structures are in main memory. So they all get affected immediately, right? So if someone induces bit flips, you can corrupt something important. You may get a wrong result. You may crash a system. And in the paper, we said that you can do all of those things. And in the paper, we also said that someone can write a malicious program that can hijack your computer. We didn't demonstrate that, but we demonstrated that you can actually write a user-level program that can induce these bit flips. And we released it. And what this program does is it takes addresses X and Y and hopefully maps them to the same bank, hopefully to the same subray. And it avoids the cache hits and it avoids the row hits to the row buffer by doing these CL flushes and accessing different rows. And it basically ping pongs hammers X and Y, I guess like this. There should be a better animation here. But anyway, you get the idea. And if the chip is vulnerable, you will hopefully get bit flips in adjacent rows. And if you want to actually make it worse, in the paper, we also showed that, but we didn't do all of our experiments with this double-sided hammering. You sandwich one row between X and Y, and that row actually becomes a double-sided victim, essentially. It's called double-sided hammer. Okay. And we showed that in real systems, you can induce these bit flips. And we declared victory because we were able to show that in major manufacturers. The key point over here is that the memory controllers are good enough to execute this user-level program such that you get bit flips that are visible in the end, right? We can do this right now. Much worse. So we published our paper and said that there's more in the paper, as we will see, said that this issue should be solved, right? And we argued that you should design intelligent memory controllers like you've seen in the past. And it was interesting because initially the paper didn't get a lot of attention. The people who really picked it up very quickly were these testing people, memory testing people. They're the ones who really care about it. They write software to test memory. You can run this software. And they basically said, they added that hammer test 13, and they actually cite our paper saying that blah, blah, the RAM modules are susceptible. That's why we added this test. The funny thing over here is that they later, because after they added this test, a lot of the DRAM modules that people tested started failing. A lot of the basically this test is not very comprehensive actually. It induces bit flips, but it's not completely comprehensive to cover all of the bit flips. Still, a lot of people complain to them that, oh, my module is failing test 13. So they had to add to their website the errors detected during test 13, albeit exposed only in extreme memory access cases, are most certainly real errors. So these are real errors, basically, they said. So they had to add an explanation saying that it happens and they're real. Basically, there's no solution to it, right? Normally, memory test programs are written to detect bad bits, right? So it's such that the operating system, for example, maps them somewhere else. Here, you're getting thousands of errors, and people are worried, right? It's very interesting, right? This shouldn't be happening, basically, another indication of that. Okay, so they have nice things that are written over here. These memory testing people were actually very proactive compared to some other people like the manufacturers. Okay, so in the paper, we said that, you've seen this also, this is a security problem also because someone can hijack your computer. We said that someone can crash your computer. I think that's also bad. But someone can hijack your computer is kind of worse, especially for security people. That's true. I agree with that. And we were actually interested in doing that. But these good folks from Google Project Zero read our paper and spent some time to replicate our results. They did. And they basically showed that you could induce these RowHammer bit flips in real laptops, and you could gain kernel privileges by doing that. Again, the idea is they were able to gain write access to, essentially, they used our user level program, and they built an attack program that induces the bit flips using double-sided RowHammer. And they were able to induce these bit flips in the page table entries that belong to that program. And they were able to gain write access or modification access to the page table of that program. It's a very nice blog post. If you're interested, you can take a look at it. It's linked from there. They also have a nice black hat presentation. They also have actually a hammer test building on our test. It's a nice attack. It's a probabilistic attack. It's a difficult attack, but it's the first attack that builds on RowHammer. Okay, later there's a lot of work that builds different attacks that show that you can take over a system. You can read data that you don't have access to. I'm going to flash some of these, I think. You can break out of virtual machine sandboxes. Google did that, actually. Later works also show that you can corrupt important data, like render machine learning inference useless because it's very inaccurate, and you can steal secret data. And this became more famous after, especially that Google's paper. It was called the DRAM RowHammer vulnerability. And one of the very famous hackers on the internet said RowHammer is like breaking into an apartment by repeatedly slamming a neighbor's door until the vibrations open the door you were really after. Right? I like this one. So people are actually quite creative in analogies, right? So if you're stuck in this room, for example, and you cannot get out, keep banging on one of the walls and hopefully magically something will open. And not the one you're banging on, though. It's interesting. Okay. And these are some papers that were written in the security community. These folks from TCuARCH, Daniel Gruss's group, they actually did some work to exploit RowHammer. They were also one of the earlier ones who read the Google work and our work. And they basically were able to write some software that could gain unrestricted access to systems of website visitors by doing this through JavaScript. Again, these are also online. You can try it. Some of these are hard attacks. This paper from 2016 showed that you could actually induce these bit flips on cell phones. This is from Herbert Boss and Kaveh Razavi. And you can actually fool the Android operating system. Essentially, you can download a program that they put, and you can, when that program runs, it will figure out which parts of your phone memory is vulnerable to RowHammer, and then it will fool the operating system to allocate a page table entry of that program in a location that's vulnerable to RowHammer, and it would hammer that location, and probabilistically it would gain access to your phone, like complete access. It would hijack your phone, basically. It's a probabilistic attack, but it's interesting that people are developing these. And people accelerate these attacks using the GPU because it's faster. People did it over the network. Again, there are a lot of interesting papers that I'm not going to cover. This is an interesting one because it's different. Its goal was not to take over a system. Its goal was to exploit some of the properties of RowHammer to leak data, meaning read some data that you don't have access to. It's not as bad as taking over the system, but it's pretty bad under some conditions. You may not want your data to be readable. And it's exploited something called data pattern dependence of RowHammer, as we will see. Okay, so there are more papers that talk about how to flip these bits with RowHammer to reduce the accuracy of the networks, neural networks, and doing this on FPGAs. I'm going to talk about that later if you have time. This is actually another discovery from Google, where they figured out that you can hammer from a far away, not just the adjacent row. It's going to be important, especially in the context of defenses. People show that error correcting codes, even if it's implemented in a real system, they can still launch these attacks. Not easy, but it's possible. And we have also shown that you can uncover a lot of the mechanisms that DRAM manufacturers added over many years to DRAM chips, almost completely, if you have an FPGA-based infrastructure to test DRAM. That's one of the reasons I guess DRAM manufacturers are trying to hide as much as possible so that you cannot build FPGAs that can test DRAM as well these days. It's good to security by obscurity is one defense, of course, but unfortunately, it may or may not work. I don't think it works. Okay. There are also interesting pictures you can find. This person is solving RowHammer in one way, right? or creating another RowHammer problem. Okay, so we wrote a lot of papers on this topic. This is actually an overview of a lot of the research that was done in 2000 until 2019. Clearly, a lot more happened after 2019, so this requires an update, but it's a very good overview that describes what has been done until then. And more recently, we updated in a shorter version, but it's not as complete of an overview yet. Okay, I'm going to skip some of these things because there's a lot more. So people have shown that RowHammer is still there in DDR5, but it's a lot harder to uncover these bit flips. This is one example over here. There are more. There was actually another paper over here that looks at RowHammer in DDR5. So there were actually 7 papers on using security last year that talks about this. And there's a DRAMsec workshop that was actually inspired by RowHammer. This was led by folks from Google and Microsoft, and they wanted to organize a DRAM security workshop so that they can actually get both industry and academia to talk about these topics more openly, because a lot happens not so openly. And as a result, you get into these situations where you get these bit flips and people need to deal with it somehow, right? So the goal of this DRAM security workshop is actually exactly that. And we organized it last year, and you can watch it completely online if you're interested. There's an interesting panel session that includes a lot of folks from industry. Okay, this was one of my students' thesis that was essentially on this topic. And it got a lot of awards, as you can see. Okay, so when you actually encounter a situation like this, there are many questions that come about, of course, right? One of the questions is, why is it happening? Not so easy for someone in architecture level to answer that. In fact, people are still just trying to figure out why this is happening in emerging technology nodes. We understand it more and more at the device level, but an understanding actually was developed more recently after these papers. There was some understanding, but it was not complete. Now there's more understanding of RowHammer. But we wanted to build another level of understanding, like not a device level understanding, but a more architectural level of understanding. What can we do in architecture to solve this problem? Because we really believe that this was a scaling problem and this would get worse. So there should be architectural solutions to the problem. So in this paper, which was the first RowHammer paper, we actually did a lot of studies to really understand what's going on. There's more that happened since then. For example, Giray's thesis built a bigger understanding of this. But let me give you some of the results from the earlier work. I'm going to pick and choose. One of the things that was interesting to us was what is from the memory controller's perspective, what is the difference between the address of a row, the address of the victim row and the address of the aggressor row? This is a memory address that the row address that the memory controller issues to DRAM. Right? And we basically examined all of these chips. This plots worst case, the chips that have the worst RowHammer vulnerability. And the distribution of this address difference on these chips from 3 major manufacturers. And you can see that in most cases, the address difference between the victim row and the aggressor row is 1, meaning they're physically, well, they're logically adjacent, right, from the memory controller's perspective. But there are some cases that are curious where that difference is larger than 1. So we hypothesized that this is because the addresses get mapped to some other addresses internally. So there's a logical address that the memory controller is exposed to based on row addresses, but internally those addresses may get mapped to some physical addresses. And as a result, because of this remapping that happens in DRAM, memory controller doesn't have the full knowledge of what rows are physically adjacent. It doesn't have a very essentially a complete map of which rows are adjacent to each other. Now this is interesting because this affects the solutions that you develop in the memory controller. Right? If the memory controller doesn't know which rows are adjacent to each other, then it may not implement very efficient solutions. Right? We're going to talk about solutions also. Of course, inside the DRAM, whoever designed the DRAM or in the subarray, you know exactly which rows are adjacent to each other. So if you have a solution inside the DRAM that doesn't have to go through the memory controller and the DRAM interface, your solution may be easier. Okay, so that's why we wanted to examine it, so that we can develop solutions on the memory controller level. Okay, so the other thing that we wanted to examine using the infrastructure was the access interval, meaning how frequently you should access DRAM such that you don't get a bit flip. I should rephrase that as how infrequently you should access DRAM, because today we're accessing DRAM very frequently, and you can reduce the rate at which you're accessing DRAM such that you cannot induce these bit flips, right? So the maximum rate is the maximum possible activate pre-charge latency. It's called TRC in DRAM, and that's about 55 nanoseconds at the time. And this is the curve that you get, which is interesting. These are real results from real FPGA infrastructures for worst chips or worst modules that we examined from 3 major manufacturers. And you can see that if the access interval is small, meaning you're activating and pre-charging as frequently as possible, you're getting more errors. And you can get rid of all of the errors that we have seen with the access patterns we have. But for that, you need to actually increase reduce the frequency of access a lot. This clearly increases the latency of access a lot, and we don't want to do that. But it's still interesting to us to examine, because if you do it very, very judiciously, very, very selectively, maybe you can actually reduce the access rate a little bit to DRAM if you're getting close to, for example, damaging DRAM, right, with RowHammer. And later, we're going to develop a solution called BlockHammer, which uses throttling-based mechanisms. And more recently, we actually improved on that with BreakHammer, that actually uses throttling mechanisms to throttle accesses to DRAM in a more intelligent way. Clearly, making the DRAM latency 500 nanoseconds is not a good idea, right? It's already too long latency. Okay. And this is another thing that we want to study, which is the refresh interval. And again, with our infrastructure, we can change the refresh interval freely because we have a soft memory controller, right? And at the time, you used to refresh DRAM every 64 milliseconds. We're talking about DDR3 at the time. DDR4 was not around yet. And this is the interesting curve that you get in terms of error count versus the refresh interval. So if you reduce the refresh interval, you're doing more refreshes, more frequent refreshes. And at some point, you will stop getting errors because your refresh interval is so small that you cannot do enough activate pre-charge pairs within that refresh interval to induce a bit flip. Right? That's the idea. And in the chips that we studied, we found out that to be able to get to no bit flips, you need to increase your refresh rate by 7x. Okay? This doesn't sound good, because if you want to get rid of every single bit flip, you need to increase your refresh rate by 7x. With double-sided RowHammer, this becomes worse. And with technology scaling, this becomes worse. Okay? As the number of activations to induce a bit flip reduces over technology scaling, you need to refresh things more and more. You need to refresh rows more and more frequently so that you can get rid of every single bit flip induced by RowHammer. So this is a bad solution. And we said that increasing the refresh rate in general in the entire DRAM is not a good solution because of this reason, basically. Now, the downside is this is the only lever, actually, that level of programmability that you have in the memory controller at the time. It's easy to change the refresh rate. And that's what industry adopted, but in a slightly different way, as we discussed. Okay, so the other thing that we wanted to understand was data pattern, because of our studies in especially retention time. We knew that data pattern is a huge deal that affects the retention time. And we asked the question, does data pattern that is inside the DRAM cells, does that affect the vulnerability to RowHammer? And the answer is yes. You get a lot more errors with a data pattern that amplifies the charge coupling across the cells. There's more to be done in this area, actually. A very comprehensive data pattern study is very, very difficult to do for various reasons, because you don't know exactly, we don't have a very good or complete way of reverse engineering exactly which cell is next to which other cell in DRAM. That method doesn't exist today. And that should be a contribution that should be made, in my opinion. And once you do that, you can actually uncover more, in my opinion, about data patterns. But this was good enough for us. We didn't need to reverse engineer everything completely. If we had to, then we wouldn't be able to write this paper, right? And we saw that there's like an order of magnitude more errors with this data pattern, even though we don't completely understand how this data pattern that we write from the memory controller gets mapped to the internal cells in DRAM. There's clearly some difference over here, right? Okay, so I guess my point is, in order to actually observe a phenomenon and say that it's affected by the data pattern, you don't have to understand everything underlying, right? Everything underlying is very difficult. You have to understand how electrons operate, and maybe not so easy also. People are coming up with new theories of how they operate, even right now, right? The fundamentals of physics. Okay, so basically, errors are affected by data stored in other cells. This complicates things, and we also said that in previous retention time papers. This complicates actually how you do the testing also. Can you actually figure out what are the worst case patterns that induce these errors? Okay, so there are other key observations in this paper. One of them says basically there's almost no overlap between cells that are vulnerable to retention failures, like refresh issues, versus RowHammer, because RowHammer is a completely different failure mechanism, and later device level work showed that it's a completely different failure mechanism. We showed that errors are repeatable, meaning if a cell fails, it's going to fail again and again and again with an access pattern. At the same access data pattern computation, it's going to fail again and again. This actually makes this security problem, because if you cannot repeat the error, it becomes harder to exploit as a security issue. Well, it depends on how you define security, of course. Right? If your goal is if your threat model is a system should not crash, then even if an error is not repeatable, you may be able to crash the system, right? But if your goal is to actually take over a system, you may want to induce these bit flips in strategic locations, like page table entries, such that that page table entry becomes modified so that you can get write access to your own page table. Then you may need to do some significant testing and also significant trials, and that requires you to be able to repeat the error. We also showed that you can have many errors per cache line, meaning simple error correcting codes cannot prevent all of the errors. This is also interesting because DRAM manufacturers claim that ECC will solve this problem. I don't think they claim that anymore. They're actually really interesting stories about this. Maybe I'll leave the stories for now. Okay, maybe I'll tell one of the stories. There are a lot of stories on this topic, and in general, how DRAM is designed. But I gave a talk in a supercomputing conference. This was in 2015, I think, 1 year after we published this paper. And I talked a little bit about RowHammer, mostly about memory-centric computing. I think the next talk was from this very senior vice president from a major DRAM manufacturing company. Good guy, actually, no problem. But I mean, he had to stick to the party line, right? There's a party line that they had to follow. And the first thing he said was, we have a solution to RowHammer. It's 3 letters. Can you guess what those 3 letters are? ECC. Yeah. Anyway, I think it's proven that ECC is not. So there are 2 reasons why ECC is not good against RowHammer. One is you get a lot of errors per cache line. Maybe on average, you get few errors, but there's many cases where you get a lot of errors. And the number of errors per cache line, or per ECC code word, I should say, that's increasing as technology generation becomes smaller and smaller. So ECC becomes a costly solution. So if you have only 1 bit correcting errors, single error correcting errors, it's not going to work under all cases. So you need to have some other solution also. You cannot just have ECC, basically. ECC helps the problem, but you cannot just have ECC. And also, I think there's another fundamental issue with ECC. ECC, in general, if you think about a principal design, I would use ECC for errors whose reasons I don't understand, and thus I cannot more efficiently prevent those errors. Right? Here, I know exactly why this error is happening. Right? There's an access pattern, and I can create some other solution to fix the error, as opposed to relying on very costly ECC, which requires redundancy in every single row in DRAM. Right? So I think fundamentally there's a problem in solving ECC. So ECC is usually put into systems to, let's say, correct transient errors, right? You get some transient error because of whatever. Initially, it was alpha particles, for example. And you don't know where it will strike. And it strikes, you cannot control it. It's a random error. And if you have redundancy in your mechanism, then you correct it. Here, it's a very different problem. Okay. That's why I don't like ECC in solving RowHammer. But I think there might be benefits of ECC in helping RowHammer solutions. The always issue is you have some ECC budget, meaning error correction. You have some error correction capability. And if that error correction capability is designed to correct error X, Y, Z, T, you may exceed the correction capability in the number of errors that you get. Right? This happens in flash memory, for example. When you design flash memory, you can always correct everything with ECC. But people don't do that because they know that this is expensive. So they build a lot of specialized solutions to correct for read disturbance, write disturbance. All of these different cases have specialized solutions. And the goal is to actually ensure that your ECC capability doesn't exceed, because there are some errors that you don't understand the reasons for, or at least maybe you don't understand, you do understand the reasons for, but they're random. Meaning you cannot, at least at this point, you don't have any other better solution, more efficient solution. So you rely on ECC. And if that error happens concurrently with this error that you could have easily prevented, you exceed your ECC capability. Right? So I think abusing ECC is probably not a good solution in general. But I think you can take advantage of ECC to improve the efficiency of other solutions to improve RowHammer solutions. Anyway, I spent a lot of time on the story, but I think there are a lot of interesting things like principal design plus making outrageous claims over here. Okay, so we also already talked about double-sided hammering, so I'm not going to talk about that. So RowHammer is getting much worse. I'm going to talk about this revisiting RowHammer paper. This recently was selected as a top pick in hardware embedded security, I think 6 years after its publication, I think deservedly. So that's good. This was part of Jeremy's PhD thesis. This actually corrected some belief. Maybe I'll talk about that when I get to it, because after we published our paper in 2014, DRAM manufacturers, of course, took some action. They didn't tell anyone what they did exactly. There was some standard change slightly. There was target row refresh. Basically, there was something that happened, and DRAM manufacturers somehow were able to convince the community that RowHammer is not a problem anymore. And the papers were getting rejected with unscientific claims saying that, oh, this is not a problem anymore. Why are you writing a paper about it? Not my paper, actually, other people's papers. So we wanted to actually examine whether or not that's a correct claim scientifically. And we did the study with devices at the time. And we found out that what is claimed is very likely not true. Meaning this problem has become much worse. And it's very difficult to solve the problem with any known solution that we know of. Okay, that was the contribution of this paper. I'm going to talk about that. So this actually enabled a lot more activity in the standards bodies to actually solve RowHammer. That's what enabled better solutions to be developed. That's the good part. Okay, we also wrote some papers with Microsoft that I'm not going to talk about. But I think the interesting thing in this paper is we wanted to ask the question, if you're a cloud provider and you're buying these DRAM chips, can you test these DRAM chips to guarantee that they're not vulnerable to RowHammer? So we tried to develop a testing methodology, and we figured out that it's not possible. So there's a lot of data in this paper. That's really interesting, I think. Okay, so this is part of Giray's thesis that looks at more sensitivities. We may get to it. And this is also part of Giray's thesis that looks at other things. So there's a lot of studies that we've done over many years to really understand what's going on with RowHammer. So HBM is as vulnerable as other chips. And these are some of the other papers that we wrote. So let's talk about solutions a little bit. I did talk about a little bit solutions, but solutions is another aspect that we covered originally. And they're actually, this is an interesting problem, because if you discover a problem like this, clearly chips in the field are vulnerable, right? You need to do something about it. And unfortunately, you have limited possibilities. If the memory controllers were programmable, I think you would have a lot more possibilities. That's what we also argued. If the memory controllers are programmable, configurable, you can solve this problem much more easily when you discover in the field. So I think having patchable, programmable memory controllers going into the future is really important for robust solutions. In fact, that's probably true for a lot of the controllers that you have in the system. You want a lot more flexible controls that you can update in the field, because you will discover these issues as technology scales, and also as you encounter situations where computing devices are used in harsh conditions. Okay, but longer term solutions can be much more, let's say, innovative. And there's still a lot of work going on over here. Interestingly, there's still a lot of claims made by the manufacturers saying that they solved this problem. The problem is not as worse. And people are still trying to reject paper for that reason. It's good to keep that in mind. But basically, in longer term, you have a lot wider range of protection mechanisms, and there should be more research in this area. So we proposed both types of solutions. We looked at 7 solutions in total, and we described one of them as the best for reasons I will describe. This is already employed in the field, both in DRAM chips as well as memory controllers. Before going into that, these are some solution approaches to RowHammer. You can design more robust DRAM chips by changing the technology, by changing the materials, by essentially, I think this is already going on, and people are trying to do that, and this is good to do, but it's very difficult to do, unfortunately. Changing a lot of things in DRAM is not easy. The second is error correcting codes. We already spent a lot of time over there. Increasing the refresh rate indiscriminately across the entire DRAM is one solution, but we already showed data that this is a bad idea if you want to get rid of all of the errors. Physical isolation is another solution. Isolate the victim rows from aggressor rows such that there's space between them. It's a wasteful solution, and it may not be easy to implement if there are other disturbance issues that we may get to. The two major solutions that are really interesting and that don't have, let's say, as bad downsides as the previous ones are really reactive refresh and proactive throttling. And the idea of reactive refresh is you count the number of activations, or you figure out which rows are rapidly activated, either by precise counting or some approximate counting, or some sampling. You figure out which rows are hammered, you identify them, and you refresh the victim rows before the aggressor row is activated more than some number, okay? Before data gets corrupted, basically. That's the idea. Identify aggressor rows, refresh the victim rows. There are many works that have implemented different versions of it. And our solution Para falls into this one. Also, it has a very low-cost identification mechanism for hammered rows using sampling. And the current standard per row activation counter is another implementation of it with reactive refresh. The idea over there is every row has an activation counter inside the DRAM, and that gets incremented in some way every time you activate it. And if the activation counter is greater than some threshold, you refresh adjacent potential victim rows. Okay? So a lot of solutions fall into this category. The other solution that's really interesting is proactive throttling, which is you still identify which rows are hammered, but as opposed to refreshing victim rows, you stop activating the row that is dangerously close to causing bit flips to other rows, okay, the aggressor rows. Basically, throttle the accesses to the activated rows. This is also very, very interesting, I think. And I think there's more to be done in this area. There are fewer solutions that fall into this domain. In my opinion, there is more that can be done by combining this with reactive refresh, perhaps. There's another set of solutions that I don't cover over here that are interesting, but very hard to justify. And I think people are finding that out also, which is remapping rows. The idea is you identify which row is activated a lot, which row is aggressor, and you remap it to some other place if it's getting too dangerously close, right? Now, the problem with that idea, I think, in general, is remapping is very expensive. So you need to move the entire row somewhere else, right? Either, especially if you do it through the memory controller to somewhere else, it's actually really expensive. But in the end, if you don't have support from the DRAM to do that movement, which we talked about, like row clone, for example, then it's extremely expensive. If you start adding support to the DRAM to do that, it becomes interesting. Then the question is this justified to do, right? Why don't you just refresh adjacent rows? Is that faster or easier compared to remapping rows? So it's good to think about it. That's why, well, it's not why I don't have remap. That was developed a little bit later. But I think it's also a harder to adopt solution. But it should be somewhere here. OK. So in the end, the solution space is actually very rich. That's why people are still developing solutions to this problem, as I will kind of go through. There are a lot of solutions that have been developed. They all have some cost. They all have power implications, performance implications, complexity implications. And that's actually interesting. For example, proactive throttling, also implications in terms of interface and security, right? Robustness. For example, if you want to implement reactive refresh in the memory controller, you need to know the mapping of rows, right? Which rows are adjacent to each other. If you want to implement proactive throttling, you don't need to know that information. So you can implement proactive throttling much more securely, purely in the memory controller, compared to reactive refresh. It's good to think about those trade-offs also. So security is another trade-off over there. OK, so what did industry do? Initially, industry increased the refresh rates because that was the only thing they could do, right? And Apple is nice because they referenced our paper over here. They issued the security release. They said that memory corruption issue known as RowHammer was mitigated by increasing memory refresh rates. Clearly, you can see that this is a bit vague. They didn't say how much did they increase, right? That's the most important thing over here. Did they increase by 10x? I don't think so. They probably increased by 2x, and probably is a strong probably over here. That's all I can say at this point. OK. So what was our solution? Our solution was not compatible with existing devices, so it's longer term, clearly. But it was adopted actually very quickly in TRR implementations. So the idea is have a low-cost mechanism. We dismissed some of the solutions as being expensive, like increasing the refresh rate, like adding per row activation counters. They're all dismissed. Well, dismissed at least initially, right? Clearly, a lot of research has built on it, so there's a lot of interesting things here. But the idea is when you close a row, when the memory controller closes a row, this could be implemented in the memory controller or inside the DRAM. You activate the neighbors of the row with very low probability. So what you're doing is probabilistically refreshing potential victim rows. That's the idea over here. And you can decide how many potential victim rows you refresh with every closing or pre-charge. And you can decide how frequently you do that based on that probability level, right? So if you're more paranoid, increase that probability level to 1. Doesn't sound very good. Every activation will cause 2 other activations for physically adjacent rows, but that doesn't sound very good, basically. Anyway, so with the level of vulnerability that we observed in those DRAM chips that we tested at the time, we said that you get a very good reliability guarantee. So essentially, probabilistic solutions are probabilistic, right? You don't have a deterministic guarantee. You have a guarantee of when you will fail. Mean time to failure is one way of actually looking at it. When does a system fail? And you can reduce the failure rate or mean time to failure of a system by increasing that probability in the end. OK, hopefully that's clear. There are also deterministic solutions that don't rely on the probability, but they require you to more deterministically determine the activation counts of different rows. Okay, so the interesting thing that in this solution is this is still the low-cost solution, very low-cost solution. You get low power, low performance overhead. We observed relatively small slowdowns. It's stateless, so you don't need to keep track of any activation counts, right? That's very, let's say, in a sense, elegant. You don't need to keep track of anything, yet you can still protect against this. And we argued that it's effective and low overhead. And this could be implemented in the DRAM chip, which DRAM manufacturers did, because there is enough slack and timing and refresh parameters, which we've shown in other work also. And this could be implemented in the memory controller, which Intel did, and AMD also did, but and some other companies also did, but they disabled later on. The downside of a memory controller implementation is we argued that it needs coordination between controller and DRAM, and the memory controller should know which rows are physically adjacent. And we argued that there should be more cooperation between memory controller and DRAM. We didn't say that, oh, you would get less secure. We kind of assumed that there will be more cooperation such that you know which rows are adjacent at the memory controller level. Now, this is possible if you remember the self-managing DRAM thing that we talked about a couple of lectures ago. If you have a self-managing DRAM, memory controller is inside the DRAM, and DRAM manages itself. So the manufacturer doesn't need to expose this to anyone, right? That's the upside. Okay. So there's some interesting story over here. This is one Intel implementation. Intel has some patents on this also. But if you Intel implemented this para, they were the first ones to implement a version of para. And you could see this in the BIOS in a server-grade system. You basically have, you can pick your RowHammer solution in the BIOS. This is not exactly what we envisioned. We didn't need any change to the BIOS. We basically envisioned that while the system is operating, this is completely transparent to the user. Memory controller corrects these errors using para, right? Or stops errors from happening using para. But here, at least there is some implementation. And the idea is the user selects their favorite RowHammer solution, not a lot of choices. This is a real system, so that's why there are not a lot of choices. You either pick hardware RowHammer protection and 2x refresh. I don't know why 2x refresh. Maybe the memory controller was not capable of increasing the refresh rate more, because I think there should be more, right? Why not 16x refresh? Maybe they thought this was a really bad idea. But if you actually click the first one, hardware RowHammer protection, then you get row activation probabilities, as you can see. So this is kind of similar to how often do you activate. So this is implemented using some sort of randomness-based probability in DRAM. So the cost of para is you need to somehow use a randomness-based probability, but it's not that hard if things are a power of 2, right? You can use some pseudo-random number generators that are really easy to implement. If you want true randomness, we have a lot of works on how to do true randomness in DRAM, but that's another question, basically. How do you implement this? I think sometimes people get stuck on how to implement it, but it's not that difficult to implement randomness under some random number generation. Okay, anyway, so hopefully this gives you an overview of what we did in this original work. And I think the argument was you need more intelligent controllers. And I think I've already said that earlier. So we did similar work in flash memory. I didn't talk about that, but there will be some flash papers that you may select from if you're interested. So there were a lot of things that we didn't answer clearly. In a single paper, you cannot do a lot of things. And I think there are some of these things that are still not done. There many effects still need to be rigorously examined, like aging is one problem, right? What happens when chips age? This is actually a really serious problem that not a lot of work is tackling because it's very difficult to tackle. It's a lot easier to write another paper on tweaking an accelerator compared to studying aging of chips, right? You can do simulation, of course, with aging. That's a bit difficult to completely justify because you cannot examine a lot of effects. But if you really want to age real chips, that's not easy. And I'd encourage people to think about it. Environmental conditions, we studied some of these. Memory access patterns, there probably needs to be more work in that area. How do memory control and system design decisions affect this sort of bit flips? That are also interesting, I think. So I think going forward, there's still a lot of room for flexible and efficient solutions. And I like this in-field patchable, reconfigurable, programmable solutions. And I think co-architecting system and memory is very important to avoid because you can fix the problem, no question about that, but it comes at a cost, right? And the cost is, ignore the hardware cost, etc. There's some performance cost. And performance cost is not just performance cost, but it could be denial or degradation of service. Someone can turn a RowHammer bit flip attack into a denial of service attack by exercising, by basically tricking these solutions to get activated as frequently as possible, and now your performance degrades significantly and your energy degrades. And actually, we have developed mechanisms like RowHammer is one mechanism that tries to solve that problem. And I think more holistic solutions going into the future need to think about these denial of service issues also. Right? Any questions? I talked a lot, but I can talk a lot in this topic. Yes. Go ahead.
Most of the on the slides were based on like the architectural level. And like, do you think, well, if there's anyway, eventually, maybe after 10 years, if there's a true solution, then do you think it will be like a more to architectural level or the device? Physics or like that?
Yeah. Now 10 years later from now?
Yeah,
I see. Yeah. I think it's probably going to be a combination. I think in the end, there will be some mechanism. 10 years down the road, hopefully there will be some better DRAM structures, like some sort of 3D mechanisms, etc. Some better designs that will be more resistant. But I don't think the problem will go away. So you will need some architectural mechanisms. Okay, you're noting that. You can come back in 10 years and tell me I was wrong, which is fine. Okay, any other questions? But people have also developed, I thought you were going to ask software level solutions, but you asked the right question. Software level solutions are much harder, like physical isolation can be done in software, much harder. There are actually papers written on those topics. They're very interesting papers. Like they use performance counters and they try to reduce access rates of programs that activate a row a lot. I think those are difficult solutions in software because the problem is getting worse and the software cannot react as fast. It's good to think about software also. No. Okay, so what did the industry do? I think this is an interesting story, hopefully. But basically, industry claimed, clearly, they developed some solutions. What they did was they actually had, in later DDR4 chips, and in some DDR3 chips also, they had some target row refresh mechanisms. This was a vague standard with no prescribed implementation. And they basically claimed that RowHammer is solved, and especially Samsung and Micron. I think SK Hynix were a bit smarter about this. But basically, they had very strong claims in their reports, presentations. RowHammer is solved, it's not a problem. They told that to all of their customers without any evidence, right? This is actually secure. They had no basis, no proof, no demonstration. Security by obscurity. Actually, in this case, it was security by assertion, right? I'm the manufacturer, I assert that I'm right, so believe me. So it doesn't sit well with scientific process, right? So of course, and they didn't really explain how, right? Of course, there's an indication. There's this target row refresh, they implemented something. And because of this, actually, industry stopped developing some of the memory controller solutions. Intel kind of believed them, and they stopped improving their solution, the memory controller. And also, unfortunately, including academics, believe that. I think this is very sad. That's why I think as academics, when we review papers, we should just look at the evidence that's out there as opposed to, I don't know, statements by manufacturers who have a vested interest in saying that it's solved. Okay, so there was a widespread belief that RowHammer was solved. There were RowHammer works getting rejected due to this belief. We actually didn't do any RowHammer work until that time. But people complained to us saying that their work was getting rejected because they were getting these comments like, oh, we solved the problem. The DRAM manufacturer said they solved the problem. Why are you working on this? Of course, we were interested in whether that was true or not. So we wanted to really look at what happened to the newer chips. Right? So that's why we revisited RowHammer. And this is the paper. And after we wrote the paper, actually, people who were doing RowHammer research thanked us. They said, it's really great that this paper is out there because that helps us to build better solutions to RowHammer. maybe their paper started getting accepted in a better way. Okay, anyway, this paper was not rejected when it was submitted. This is one of the, I don't know if it's few, but one of the papers that got accepted right away. I think good work should be like that, but that's not the case all the time. Okay, so what did we do? Basically, this is probably the largest device level study to date of RowHammer. We studied essentially, we wanted to actually understand two things. How is RowHammer vulnerability scaling in newer chips and different types of chips, LPDDR4 and also DDR4 and also DDR3. And we also wanted to understand whether the claims are true. So meaning if the device level, at the device level, can you actually have a RowHammer vulnerability that's getting better? Because there's some claim that there is a solution. At the device level, has it become better? And also, is it easy to solve the problem with known methods at the architectural level? So this did all of those things. And for this, we need to build a lot of infrastructure. We adapted SoftMC to DDR4, which later became DRAM vendor. And we also had an in-house testing hardware for LPDDR4 chips, which was nicely sponsored by a $1 trillion company who was really interested in these things. And whether those claims were also true or not, they should remain, let's say, anonymous. Although you can probably figure out by looking at where some of these people who are authors worked. Okay, so essentially, these are actually very interesting infrastructures. LPDDR was more limited, but we had actually access to some of the interesting memory controller features that we wouldn't otherwise have access to. Okay, and you have fine-grained control base. This is actually the DDR4 infrastructure that we built looked like this. And we tested almost 1,600 DRAM chips from different generations, 3 major DRAM manufacturers, of course, 3 different DRAM types or standards, 2 technology nodes per DRAM type, so that we can understand how the things are scaling, old technology node and new technology node. Again, you can read this in the paper. These are the key takeaways from all of these studies. Basically, we found out that newer DRAM chips are much more vulnerable to RowHammer at the device level. If you turn off the mitigations, you get a lot more bit flips that are happening earlier. So the fundamental vulnerability became much worse. Meaning, yes, maybe something happened that prevented it from becoming much, much worse, but it became much worse, which meaning that it's difficult to develop a solution, right? So there are new chips whose weakest cells fail after only 4,800 hammers. This is double-sided, so it's actually a total of 9,600 hammers on both sides. Still, that number is much smaller than the 139,000 number that we had in 2014 paper. And you get more bit flips in more rows in newer technology nodes and farther away from the victim row. And we also did some simulation studies based on the results that we got that show that existing mitigation mechanisms that are out there, that are published, are not effective at future technology nodes. So we're going to look at that. So these are data from real DRAM chips from 3 major manufacturers. On the x-axis, you see the hammer count, how many times you hammer a row. On the y-axis, you have the error rate, essentially, bit flip rate. And these are different types of DRAM chips, old, new, as you can see. And you can see that if you focus on the DDR4 results, bit flip rates increase when you go from old to new technology node generations. So you can see that the blue curve shifts to the left and becomes higher, goes up as hammer count reduces, right? So hammer count reduces from right to left, meaning that the first bit flip happens earlier and you get a lot more bit flips at a given hammer count. Earlier meaning at a smaller hammer count. Okay, and that's very consistent, as you can see. And DDR4 was the easiest to analyze because we had DDR4 old and new chips from all major manufacturers. You can see that we had LPDDR4 from only a small fraction of the manufacturers. Okay, anyway. So basically, bit flip rates increase with technology generation, meaning fundamental device level vulnerability became worse. Okay, so we also did this simulation study where we tested all of the interesting mechanisms that were developed until then. And we actually plotted how they fare as the technology scaling becomes worse. So here you see increasing the refresh rate, para. There were also some other mechanisms. Some of them were not easy to scale to a smaller technology. So you can see on the x-axis, the number of hammers required to induce the first RowHammer bit flip, in this case, going from left to right, is worse. Technology scales. And these are the real numbers that we obtained. DDR3 old chips. That number is over here. DDR3 new is here. DDR4 old is here. DDR4 new is here. LPDDR4 old is here. LPDDR4 new here. So as you go from old to new, we're marching from left to right, as you can see, right? So the vulnerability is becoming worse. And you can see that increasing the refresh rate. This is on the y-axis, you see normalized system performance. 100 is you don't lose any performance because of the RowHammer mitigation. 0 is your system stops running because of the RowHammer mitigation. And increasing the refresh rate is getting close to your system stops running to get rid of all of the bit flips. So that's a bad solution, as we discussed. Para is not so bad, but it doesn't scale very nicely. So if your vulnerability goes to, let's say, you get a bit flip after 1,000 hammers on each side, that's 2,000 hammers total. Your performance impact on these workloads, on average, is about 25%. Doesn't sound good. I don't want my performance to reduce by 25% because I want to protect against RowHammer, right? So we argued at this point that para is not a good solution as if the scaling becomes worse and worse. Some other solutions are actually even worse. They don't scale very well. Twice, if you make it ideal, which becomes extremely expensive, it scales better. And even the ideal solution has some non-idealities that doesn't make it scale better. But no, there is a huge difference between the ideal solution and what scales the best, which was para at the time. Later works actually improved upon para. So that's good. We have more scalable solutions right now. Okay, so I basically said that if the scaling we observed continues like this, we don't have solutions to this problem. Okay, and we basically argued that there's significant opportunity for developing a RowHammer solution with low performance overhead that supports lower values. And I think this is a worthy direction to continue exploring. So this paper demonstrated that RowHammer is a technology scaling problem. Finding a good solution to RowHammer is difficult, and it will become more so. Any questions? Unfortunately, the study needs to be repeated, I think. Well, maybe fortunately, depending on your perspective. I think this was 2020. In 2026, clearly there are newer chips. It's good to understand where RowHammer is. And we have also other redisturbance mechanisms, RowPress, which we may get to, but you already know what RowPress is at a very high level. So it's good to repeat this sort of scaling study. The problem is it's very difficult to do this sort of scaling study right now because it requires an infrastructure, multiple infrastructures, some of which is already there, like DDR3, DDR4 is easy. The difficulty is that DDR5, there's no good infrastructure for testing DDR5 in the way we tested it. People have developed some other infrastructures, but it's very difficult to see the device level vulnerability today because you cannot turn off, for example, error correcting codes. You cannot turn off some of the mitigation mechanisms. So it's difficult. So that's a good research project, actually. How do you actually look at, repeat the study in 2026? And I'm very curious about the findings because I don't know the answer. My guess would be the problem has become worse. How worse is something that needs to be quantified. Okay, so this is interesting. Basically, these are the reported HC first hammer count to induce the first bit flip in a device, lowest values since 2012 to now. So if HC first is infinite, all is good. You don't need infinite. You need just greater than the refresh, the number of activations your refresh rate allows. DDR3, it was 100 plus thousand. But in ISCA 2020, we had better access patterns, like double-sided, better reverse engineering, etc., and you get actually lower to 24K. And you can see that the lowest number that was published over time is 4.8K. Later, we did some HBM studies. These are actually HBM devices with higher node size. So you get 14K, which is actually pretty low, as you can see. 14K is much lower than 139K. So there needs to be more studies of HBM devices also, and that's also becoming harder and harder. Okay, nope, not this one. So I think one of the things that happened with revisiting RowHammer and also what I'll call trespasses, there was a change of belief in the community. So there were actually patches. DRAM manufacturers announced at some point RowHammer free DRAM chips. There was a misconception. And I think we had to correct that misconception. And this also enabled other studies like RowPress and I think PRAC, which is per row activation counting, and also VRD and column disturb. So there's more work that needs to happen there. I'm not even showing the RowHammer mitigation papers that happened in 2020. I think I have some slides that I will flash, or maybe I'll talk about some of the solutions. But essentially, there was a sad part over here in research where little happened. And I think this is not good because people were actually developing solutions over here, except they were getting rejected. Good to think about that. Okay, so revisiting RowHammer actually was part of the thing that fixed the wrong belief. It had a lot of impact. We shared this with manufacturers plus large companies like Microsoft, Google, etc. And they pushed the manufacturers to actually do something about it. So this data was very useful because no one had the data. That's the interesting part, right? Maybe DRAM manufacturers had the data, but they didn't share it with anybody. Right? I may be harsh on DRAM manufacturers, but they have a good reason. But I appreciate their efforts because they actually have a hard problem at hand. Manufacturing these things is difficult, but I think some more openness and a bit more open discussion, and also a better interface inside the DRAM can solve these issues. Like if they adopt the self-managing DRAM, I think DRAM manufacturers will become a lot more free. And they can actually solve these problems much more easily, right? Okay. Any questions? Okay. This is another work that we did concurrently. And the idea over here was to actually test the claim directly. Meaning, can we actually induce these bit flips in real devices that are claimed to be RowHammer free, right? Without let's say, looking at the device level vulnerability. And this is also a hard study to do because a lot of people wanted to do this study, but it was not possible if you don't have an FPGA-based infrastructure to really reverse engineer what's going on in DRAM. So we collaborate with people who are writing attack papers on RowHammer, like Kave and Herbert Cristiano. And we wanted to understand whether we can bypass these mitigations. Right? There's some mitigation. You've seen this picture before. If you can actually find a way of bypassing the mitigation, you can use bit flips, then you basically have proven the claim is false. Right? So this was the first work to show that TRR protected DRAM chips are actually vulnerable to RowHammer in the field. I already said that. Mitigations advertised as secure are not as secure. So the way we did this was actually to introduce a many-sided RowHammer attack. And the idea is, the hypothesis is that DRAM manufacturers did something internally to protect against RowHammer. It could be, and we hypothesize that they were doing some internal tracking of rows, either probabilistically or exactly with tables. Exactly. And we could somehow bypass this. And if you were using tables, you could overflow these proprietary TRR tables. We didn't believe that they were tracking every single row, for example. If you're tracking, let's say, only 4 rows per bank, if you hammer more than 4 rows, you would evict some of the counters in one of these counters, or all of the 4 counters, and you would mess up with the tracking mechanism that's inside the DRAM, and you could actually induce bit flips. That's the idea, basically. Reverse engineer just enough in DRAM to be able to bypass these internal mitigations to induce these bit flips. And that's what we did, essentially. We actually reverse engineered the memory controller-based mechanisms also. And we actually released an automatic tool that can effectively create many-sided RowHammer attacks. And later works in the security community built on these tools to do even more attacks using fuzzing, using different mechanisms, etc. So the idea is you don't hammer 2 rows, have a double-sided attack, you hammer 1 more. That's a 3-sided attack. It could be a 4-sided attack. You could have a 20-sided attack, right? 20 rows you hammer. So hopefully you will overflow the tables. In this work, we didn't completely reverse engineer. That's the next work that I will talk about. But basically, these are, again, results from real DRAM modules for example, to induce a bit flip in this module, you need to do a 7-sided hammering. You hammer 7 rows. And you have some curve, because there may be some replacement policy that is there in the table. There may be some probabilistic mechanism that's also there. Who knows? The key for us was observing this bar to be greater than 0. The number of bit flips greater than 0. And if you get the number of bit flips greater than 0, that means that the mitigations are not secure, right? And we tested some number of modules. We were not able to bypass the mitigations in all of them, but we were able to bypass the mitigation in enough of them, and for all major manufacturers, that we declared victory. So 13 modules out of 42, which is a small fraction, but still an important fraction, right? Because the claim was we've solved the problem, right? Okay. And collaborating with the security folks, they had already attacks to take advantage of RowHammer. We were able to show that these modules that are used in real phones, you can actually induce these bit flips. And you can actually do these attacks relatively quickly on these DDR4 chips that are claimed to be resilient to RowHammer, right? Okay, so that's the idea over here. These are the key results. And essentially, these were just scratching the surface, in my opinion. And the tool was not exhaustive. And there was a lot more room for uncovering more vulnerable bit flips. And I think what this paper also showed that was security by obscurity is likely not a good solution, because someone can reverse engineer things, right? And I think smart people can reverse engineer even more. And that's what we wanted to do after that. But these two papers together caused the community, especially the buyers of DRAM, to push the DRAM manufacturers to do something more serious about it. They got together, they formed the RowHammer task group. They wrote these 2 abstract white papers, I would say. But they had some high-level ideas over here, like system-level RowHammer mitigation. But they cited a lot of the revisiting RowHammer work, for example. They used the terminology like HC first, etc. So it's very interesting that your work immediately gets adopted, right? These are within 1 year of the publication of the work. In less than 1 year, actually, March 2021, as you can see. And the paper was published in June 2020. So it's interesting. These are not complete solutions, but the good news is this task group was reformed again, so that you would do hopefully a better solution. And over time, I think iterations led to the PRAC solution, per row activation counting, which we will talk about. It's a better solution. The question is it the best solution? I don't believe this is the best solution. I think this is still quite expensive, having every row having an activation counter. The good part of the solution is now you have computation capability inside the DRAM chips in a much more extensive way than the previous solutions. Any questions? Okay, one of the interesting things that we wanted to do was, can we actually do more? And what are the implications? Can we actually push these DRAM chips to fail earlier? And that's what we did in this work. It's called Uncovering TRR. This was part of Hassan's PhD thesis. And this work has a very interesting key insight that allowed us to actually uncover more of what's going on inside the DRAM chip. So the DRAM chip is kind of like a black box, right? Internally, it issues a target row refresh once in a while. And the question for us was, when does this target row refresh to fix RowHammer get issued, right? So basically, the idea is we wanted to develop a new methodology to uncover the inner workings of this target row refresh mechanism. The idea is, at some point, a row gets refreshed. How do you figure out that that row gets refreshed? This is where a lot of the understanding of retention times was proved very useful. So we developed a long body of understanding of retention times. And one of the things that you do when you try to understand retention times is, how long can a row retain data, right? You identify some rows. Oh, a row can retain data much longer than a refresh interval. You find those rows, and you also find those rows that will lose their data if they don't get refreshed more frequently. Basically, a row, you change the retention, you change the refresh interval, and what you would expect is a row will lose its data if it's not refreshed by an internal mechanism, right? That's the idea. So you profile the retention time of rows, and you find some rows that are actually going to lose their data if it's not refreshed, because you're not going to refresh it through the memory controller. Someone needs to refresh it internally. And you do a RowHammer access pattern. This needs to be crafted very carefully, but you craft it very carefully. And if you don't lose the data in that row, then you know that somebody refreshed it internally. Right? It's not you, because you're designing the memory controller. This is a soft memory controller that we designed in the FPGA. It must be the DRAM chip. That's the idea. So the fact that the row didn't lose its data is a side channel that provides information about what's going on inside the DRAM chip. And by doing this repeatedly with different access patterns, you can figure out which rows get refreshed, how often do they get refreshed, whether they're in the same bank or different banks, whether they're in the same subarray. So you can uncover a whole lot of information about this. It's very tedious, not easy, but it's possible to uncover a lot of information using the side channel. There's a nice side channel, basically. We're using retention failures as a side channel to detect whether a row is refreshed and when is it refreshed. So we uncovered a lot more, basically, about different manufacturers, mechanisms. You can see that some of them are counter-based, some of them are more probabilistic activation-based. You can see that some of the tables have a capacity of 16, some of them have 1. We didn't put enough effort because at some point this gets very boring. So some of these are unknown, unfortunately, but you could actually uncover these with more effort. There was more complicated mechanisms because this manufacturer, Micron, implemented a mixture of mechanisms over here, and that made it this a bit unknown. And you can see that whether the mitigation mechanism is per bank or across all of the banks, you can see that when this mitigation mechanism actually gets triggered, how many neighbors are refreshed? Is it 4? Is it 2? Is it 4? So you can see that there's no consistency. And once you do that, what is the fraction of vulnerable rows and maximum number of bit flips per row per hammer? So that's interesting, right? So you can figure out a lot of information. Also HC first. Although this HC first may not be the lowest HC first, right? Because we're really trying to fool the device. This is the HC first we were able to induce by all of this methodology. Does that make sense? Lower device level HC first may be lower than this. It's good to think about that. Okay. And we also showed that ECC is ineffective. You can have up to 7 RowHammer bit flips in an 8-byte data word. Okay, but we knew that before. It's just reviewers keep asking, what about ECC? So you have to do this analysis, you know. It's very interesting that reviewers keep asking, what about ECC, even though there's a whole body of literature that says ECC is not effective, and you have to still show it. It's kind of boring, right? Okay, anyway, that's the state of the art in reviewing. Okay, so there are a bunch of other things that are really interesting in RowHammer. I cannot cover everything, I think, but RowHammer has many dimensions. This is also part of Girai's thesis. We wanted to understand the effect of temperature, the effect of aggressor row active time, and physical location of the DRAM cell. And if you know more information, if you understand more about RowHammer, you can use it from the perspective of the defender and from the perspective of the attacker also. So this sort of information helps everyone. Of course, it's better if the defender knows this information earlier. If the attacker figures out information faster, then they can develop better attacks, right? And this is one of the reasons it's really important to actually publish work on this topic, on this sort of topic, security-related topics, both attacks and information about understanding attacks quickly, because that levels the playing ground, right? Because inherently, an attacker has a good incentive to attack. You may not agree with that incentive, but they have a very good incentive. And they're going to do probably a lot of things, especially if they're a very powerful attacker, to figure out information. Whereas defenders are much more distributed because there's a much bigger attack surface that they need to defend. And they have a lot of other things to deal with, like designing the system, making it work. And as a result, they don't have the same incentive to discover, because there are many, many attacks also, right? So the research in security needs to consider this. And sometimes people say, people should not publish attack papers. People should not publish X, people should not publish Y. And they also reject papers for no good reasons, let's say. But there's a good reason for doing this quickly and publishing these things quickly because that levels the playing ground, right? If I can do it and I can figure it out, an attacker who has an incentive with billions of dollars, potentially, it's also possible, can figure it out. Maybe they already figured it out. Right? It's better that a white hat attacker or white hat researcher publishes it and puts it out so that the playing field is leveled. Everybody knows that information. I think I had to do this because this is really important. There's always this question, oh, should you publish attack research? Is that good? I actually also don't believe that there should be very long embargo times when you find a new vulnerability, for example. Companies like enforcing these, but that actually works against the public interest, let's say. Okay, anyway, with that diversion, we wanted to understand these effects. And we found some interesting observations over here. We tested a small number of chips because these are very extensive testing, very long and hard to do. And we found out that a RowHammer bit flip is more likely to occur in a bounded range of temperature. And this temperature range changes depending on the cell, meaning that we don't understand the phenomenon. That's what it boils down to. We don't quite have a good relationship or good theory of how temperature affects these RowHammer bit flips, and that's still the case, unfortunately. I think there are multiple competing effects with temperature that makes different cells behave differently. Some reduce the RowHammer vulnerability, some increase the RowHammer vulnerability. As a result, you get this very weird distribution of different cells having different vulnerable ranges at different temperature levels. The second one is very interesting because this led to the discovery of RowPress. We thought it was actually an extension of RowHammer. If you keep the row active for a longer time, we found out that you get a lot more bit flips. We didn't know that this was a very different effect, but we proved that this was a very different effect in the RowPress paper. So this paper is actually very important in that it enabled RowPress. And also we found out that there's spatial variation in the vulnerability of different parts of the DRAM. So now if you know all of this information, you can create more effective attacks and more effective defenses. I think it's difficult to exploit the first one, but it's a lot easier to exploit the second one and third one for better attacks and better defenses. Okay. So for example, we showed that if a row is kept active for longer, you get significant reduction in number of activations to induce a bit flip, because this induces some different type of read disturbance. We didn't think that it was, or we didn't know that it was a different type of read disturbance. We just said that you would get much more vulnerability if you actually keep the row active for a long time. Now, if you do this, as an attacker, you can bypass defenses that are configured to be less aggressive. And as a defender, you need to basically improve your defenses, right? That's the idea. The other spatial variation is interesting. Gira actually wrote another paper in HPCA 2024, a more rigorous study of spatial variation of RowHammer effects. This was the first initial study. And basically, we showed that about 10% of the DRAM cells are much more vulnerable than the remaining 90%, right? You can see that HC first doubles in the remaining 90%. And if you have a heterogeneous mechanism that's aware of this variation, you can change the aggressiveness of your mechanism. You can reduce it for 90% of the cells. And as a result, you can reduce the area and energy impact of those mechanisms. I think there's more work to be done in this area. This is not exploited well in systems. Okay, I'm going to skip the leveraging variation with temperature because I believe this is actually quite difficult to do. Okay, there's more in Girai's talk. More RowHammer analysis. I think we will start with that next week. Any burning questions? Okay, then we're done. See you next week. And look at your email for papers and select as soon as you can so that we can schedule everyone for paper presentations. Cool, take care.